A very good afternoon or good morning to everybody who's attending this webinar today. My name is Arvind. I'm the application engineer at EM about transformers. Okay. Now really the topic is titled Transformers, Challenges and Opportunities in Electrothermal Simulation for Optimal Electric Performance and Thermal Management. The agenda that we have today, we're going to start out by spelling what are the current challenges by designers and engineers in this particular industry, and what are the limitations that the current models of testing have, and then we're going to explore how simulation could be an option for designing transformers. We're going to take a look at a case study. This is one of our customers from Portugal called FASEC Transformers, and we can quickly take a look at how they benefit from simulation in their designs, and we're going to compare the simulation with the test cells, and then we will also do a short demonstration and end this session with a question and answer session towards the end. I want to bring to your notice that should you have any questions during this presentation, you please feel free to type it in the chat window. My colleague Adam at the end of this presentation will then go over those questions and we will answer them towards the end of the presentation. But as and when you find questions in your mind, please feel free to type them out in the chat window that you see in your GoToMeeting setup. Let me start by what are the challenges faced by the industry today. First of all, transformer, as you may know, is a very old electrical component, electrical machine. I mean, it's almost 100 years old since the first transformers came into existence. Being such a very proven and old technology, really what could be some of the challenges that engineers today are facing? Okay? The first thing is, there's always a strain on the rating, and transformers are now designed to have much higher rating, but at the same time there's a constraint imposed by the size and the weight and so on. So basically the challenge is to make large as possible. Then the next one is, how do I predict the performance and the loss that is there critical designs of and so on. It's important to understand how the performance of your transformers or your various designs of your transformer. And obviously transformers, the question of thermal management becomes very important. How do you now predict what could be the temperature distribution inside your transformers and so on. We talked about losses a little earlier. One of the main objective is to reduce the eddy losses, eddy current losses induced, or the induced current losses in a transformer. And how do you go about doing it? How do you measure losses and so on? And finally, elimination of hotspots or temperature areas. You need to smoothen that out or eliminate as much as possible. The idea is to have a transformer working in a very ideal condition where the temperature is under control and so on. And obviously other parameters like noise and vibrations also come into play while as some of the challenges in the transformer industry. Now, limitations of physical testing, obviously, the larger the transformers that you design and the more complicated it becomes, the physical testing becomes really prohibitive and also quite limited as far as its usefulness. Okay. In this picture, you can see, maybe it's not very clear, but you can see these blue, these are thermal sensors. Basically, they are stuck. They're just attached to the metal, and then that basically gives you the temperature reading. Okay. And here you can see the location of the sensors and so on. I mean, these are some of the things that people do to test their transformers, is basically to measure the temperature at various locations and to see if it meets the performance criteria or not. So as you can see from that image, obviously the limitations are quite pronounced and obvious. You know, the sensors and testing equipments, you know, it doesn't come cheap. You know, they're expensive. There is also a physical limitation of how many sensors can you actually have. You know, can you do by with 50? Do you want 500? What is the, you know, where is the trade-off? Okay, and all of this would be very nice if I knew where the hotspots or which are the problematic areas inside my design. If I knew that prior hand, then I can place these sensors, you know, quite optimally in those locations, and I would be able to have a much better testing of my designs. But unfortunately, that's something that's not very easy for engineers to predict. So the location of the sensors, where to locate them, is always going to be a big challenge. Okay, and finally, you know, you can measure things like maybe flux, you can measure temperature, but really, you know, how can one accurately measure the losses, basically the eddy current losses and core losses and so on? You know, there are some challenges involved here in this. Okay. And these are some of the limitations that the industry faces today. We talked about losses in the transformer, basically the core loss of the transformer. And why are those losses very important? Okay, loss actually means a loss of dollars. Basically, when you lose energy in the transformer, or which is basically dissipated as heat, it means a loss of dollar, because energy, that electrical energy, is converted into heat, and heat needs to be dissipated, and hence there's some inefficiency. So that's inherently losses, means loss of money. But you know, I think engineers have also, through their experience, they have quantified this loss, and according to the industry standards, the losses is about $6,000 to $8,000 for every kilowatt of core loss that you experience. Okay, and imagine, multiply, this is over the lifetime of a transformer, and multiply that by the hundreds and thousands of transformers that work all over the world, and if you can cut losses by 10 or 20%, that's dramatic savings right there. Okay, so it's very important to study these losses properly and do designs in such a way these losses are minimized. And what are the types of losses? We have copper loss, or this is the winding loss, and we also have the core loss. And now we come to the important topic, as you know, how can simulation actually help this industry? One of the first things simulation can do, and you will see that in the live demonstration later during the presentation, is it can help you to visualize very complex electromagnetic field, not just on the metallic parts, but also inside. You know, you might be having an oil-cooled transformer, so you will be able to see what are the magnetic field or the flux that is there inside the transformer, outside the transformer, and on the metallic surface as well. So so the ability to visualize complex electromagnetic field and temperature distribution, etc., throughout your geometry toward the domain is a very big advantage, which is not possible by naked eye during physical testing. Also, modern packages today, simulation packages, will be able to calculate all the losses in the transformer, the core loss, the winding loss, etc. Okay. Simulation can also take into laminations in the core. And obviously, one of the biggest improvements that has happened over the many years is the ability to have laminated cores, which actually reduces the losses in the lamination in the core, and the simulation can actually capture the laminations. So you can have realistic simulations which take care of the laminations at the core as well. Finally, some amount of multiphysics capability is available in the simulation. So basically, right from the electromagnetic field, the induced currents, which is dissipated as heat. So one can compute what's the temperature distribution in your model, and also from the temperature distribution, one can also compute things like thermal stresses and so on, displacements, strains and so on. So the multiphysics capability of simulation enables users to study various properties involved in their designs, okay, like electromagnetic fields, magnetic fields, temperature fields, thermal stress fields, strain fields, etc. And obviously simulation is extremely useful during the product development stage because it aids the engineer to test various design parameters without actually investing a single dollar in making a prototype or something. So, and that's very useful during product development stage. Now I will move on to the case study example that I wanted to share with you. This is one of our customers in Europe. It's called Efasec Transformers. They're a big company. I think they're worldwide. And you know, the case study that we want to take care of is a very large transformer. It's a 3-phase 580 MVA type of transformer that's categorized as a very large size transformer. Okay. So this is a case where they wanted to do some new product development, and this is where they're going to use CAD and simulation to do that. Okay, what was the objective of using simulation is they wanted to minimize the testing that they do. Okay, and also they wanted to reduce the time taken for them to bring out a new change in their product, and from the design all the way to the release of the product. So these were some of the challenges they had, and they wanted to overcome using simulation. Okay. What did they do? Actually, they wanted to test out a few laminated core designs that they had, that design team had come out with, and also they wanted to really understand the thermal management. And finally, they wanted to see if they can reduce some weight of the metal used here. Basically, the shield and so on, the thickness of the shield gauge. They really wanted to see if those things can be reduced a bit or not. Well, one of the things you know is the ability of simulation today in today's world due to the resources that are available, basically as a computer resources, as well as the accuracy of the simulation products today. The good news is simulation was found to be extremely reliable for this company. Okay, you can see here various sensors that were correlated along with the simulation results, and the error was found to be less than 2 or 3% between what they observed during their testing phase and what the simulation results they obtained from EMS product. So here is a thermal mapping. You can do the same. This is the temperature distribution that you see in the computer, and here are some of the sensors, a few sensors, and how did they compare those locations compare with the simulation results. Well, as a conclusion, you know, their engineers had the confidence that now the simulation results compared well with the test results. And the new product line with improved laminated core was actually released, and that was mainly possible due to simulation, and the time taken and the amount of money spent in releasing a new product came down drastically. Now simulation-based product development is now the standard approach used by this company. Okay, so all of their products now are all of their new designs, etc., and also their existing products are always being improved, and thanks to simulation they're able to do that, and they've actually institutionalized this process. Okay. And here now they can have much better intimate understanding of their designs. Now I'm going to take some time and go over the product demonstration so that we can quickly see what's the philosophy of CAD embedded simulation inside SolidWorks and EMS. You know, I'm going to just take an example of a very simple 3-phase transformer here. We have a core which is a laminated core, and we want to understand what are the losses in the core when the transformer is under some kind of a open circuit type of condition. Okay. So I'm going to go ahead and share my SolidWorks with you. Okay, so basically what is the philosophy of integrated electromagnetic simulation inside CAD? Okay, the idea is to be able to do your designs right inside SolidWorks. For example, your core, your coils, your etc. are all done using SolidWorks as the main CAD program, and you can do your simulations right inside SolidWorks here. So without ever leaving the interface or the SolidWorks window, you are able to have both the CAD as well as the simulation inside one environment, and that means improved productivity. That means no loss of design drawing, I mean your design intent, etc., due to translation of files between various programs and so on. And finally, any design change that is being done is automatically captured inside simulation, thereby again enabling people to do multiple designs without loss of much productivity. Okay. So as far as the simulation is concerned inside EMS, the simulations are organized as what we call as studies. Here you see a study here. It's a three-phase cylindrical transformer study. We have all the materials that are organized here. So for example, the core here is made up of, I'm going to edit the material, it's made up of a material that has a core loss curve that's specified here. It is also a laminated core. The thickness of the lamination, the density, etc. is specified. The electrical and thermal conductivities are specified, as well as the permeability of the material that is made, that the core is made of. Okay. Now I want to just emphasize here, while we have this topic, is EMS comes out with its own material library here. As you see, it comes standard with the product. So here you have a lot of materials like ferromagnetic materials are there, materials, steels with its own BH curves, they are available, and also as you see a few core materials with core loss curve is also available inside the material database. Now this is a fully customizable material database, so which means that you as a user can actually add your own materials, your own curves, etc., and use that for simulation. Now you assign, the first step is to create a study. The next step is to assign materials. So here I assigned a material to the core. All the coils are made of copper, so that's a conductor material, so all the coils are made of copper. So all of them are assigned a material copper. Then everything else is air. So you have air, that this is the air region between the two coils. Then you have an air that is that's there outside. So the main difference between a solid model and a model for electromagnetic simulation is the ability to model air. So air geometry is just modeled as another solid model, and you can use that for simulations. Let me go ahead and hide the air. And why is air very important for an electromagnetic simulation? Because as you know well, the magnetic field exists not just in the metallic part but also in the air around it. So and it's very important to capture and study how the fields vary in the air region around your transformer, various parts of the transformer, and hence it's important to model the air. Okay. Okay, we're going to go ahead and continue. So the next thing is the ability to define coils. Okay, so here we have a wound coil of a transformer, and it's very easy to define coils inside EMS. You select the part or the assembly which the coil is, which makes up the coil. You select the phase in which the current enters. Okay, here as you see with the arrows, and it's a complete coil, and you just specify the number of turns and what is the RMS value of the current per turn. Okay. So similarly we do that for the 3 different one coils, so one coil 1, one coil 2 and the coil 3. Okay. So each of these coils are now, it's because it's a 3-phase transformer, there is a phase difference between the currents entering each of these coils. Okay. So after specifying that, you go ahead and these are your secondary coils, and here too you just specify the coil, the phase at which the current enters, and because this is more like an open circuit, I'm having an RMS value of 0. So it's some kind of an open circuit type of simulation to understand what is the core loss and what is the temperature distribution, etc. in the transformer. So we just have this as 0 volts. So you can do the simulation as a closed circuit, open circuit, or you can also do it under loading conditions. Okay? If it is under loading conditions, you would specify what's the per secondary coils current and the number of turns. And this is as far as setting up the coils. And finally, we have to set up some kind of a convection thermal boundary condition. Here I'm choosing all the surfaces that are exposed to air or oil. In this case it's air-cooled transformer. I'm just specifying a simple convection boundary condition. Here I specify what's the convection coefficient and what's the ambient bulk temperature of the ambient air. Once all of this is specified, it's time for us to solve the problem. And I have my results organized as result table in the result table. Now I want to bring to your notice just one thing before we look at the results. This is a finite element based program, and you have so basically what the program does is it first divides this model into what is called as finite elements or mesh. So the ability to mesh the geometry. We have automatic mesh generation features inside the program. So any type of geometry that you create in SolidWorks will be automatically meshed, and then you can look at the results. So let's now focus on the results. What are the various types of results that one can obtain from EMS? So the results are organized in what is called as a result table. So here is a result table. And inside the result table you have many. So for example, the inductance of the coil, all the coils are calculated, the inductance matrix. You also have the current, the induced currents in the various coils, okay? The induced voltages in the coils, and the most important thing here is the losses. Okay? So we have a table which brings out the losses. So if you look at the core, here is the core loss. The core loss is about 900 watts, almost close to a kilowatt is the losses in the core. And we also have the ohmic losses in the coils. Due to a very small amount of current, about 5 amps, there's not much ohmic loss that you see. It's about a milliwatt or something. I mean, it's close to 10 milliwatts is the ohmic losses in the coil. Understandably so for very small currents. But if you see the core loss, that's the important value here. It's quite a value. It's almost about 982 watts is the core loss. Okay. So one can actually study what's the core loss of my design right from looking at this table. Okay. And because this is a 3D simulation, so one can visualize things like magnetic flux, etc. In a 3D space. So here I have a plot of my magnetic flux density as a function of the phase angle at 0 phase. This is the magnetic flux density. So another good thing is you can isolate regions where you want to see. So I want to just show my magnetic flux density right in my core. I can take a look at it. So here you see the magnetic flux density plotted as a function of the phase angle in my core. Okay. There are also several other types of plots that are available. So as I can go ahead and look at inside my model. So we have what is called as a section plot, which is what I'm going to go ahead. I'm going to now take a look at my section plot of my magnetic flux density. So this helps me to visualize my flux density inside my model. So how does it look inside my core? So I can go ahead, I can look at it, and I can move this section around. It will dynamically move. So you can see that this section can be moved dynamically and one can study. Might be a little bit slow coming through the internet, the dynamic movement, but you can see that. So you can have a section plot that will help you to see inside the model. Okay. And one can also now, as we saw, the thermal results become very important. I can now take a look at my steady state temperature distribution inside the transformer. So this is my distribution of temperature inside my in my core and in the transformer. So notice that about it gets almost close to 339 Kelvin is the temperature here in the core. So I can now just isolate and take a look at it only from a perspective of just the core. So this is how my temperature is going to look in my core. So it's you can see the hot spots in the core and how it is going to be and so on. Okay. So I can also take a look at change the units. So if I'm more comfortable with Fahrenheit units, I can change it. So about 150 Fahrenheit is the maximum temperature attained in the core. And I guess that's quite acceptable as far as the heating is concerned. But you can also really visualize where in the core are my hot spots, how much of what is the temperature. So I can actually probe in the various locations. I can see what my temperature is at my various locations and so on. So EMS has a whole lot of post-processing features that can help you visualize results. You can see magnetic flux, you can see the field intensity, you can also see the current density. For example, how is my this is the induced current here in the core. So you can see the current density in the core. So obviously there is current flow density flowing in the coils, but if I am going to go ahead and isolate just the core, so here is the current density of this core. Okay, so now last but not the least, I'm going to go ahead and take a look at a report feature inside EMS. EMS has this feature to automatically create reports. So I can go ahead and create a report inside EMS. So I can select what I want, maybe a description, the view of the model, the materials, the coils, my result table, maybe my flux density, maybe current and so on, and conclusion. So I can have a report, automatically generated report, either as a HTML or Microsoft Word. Okay, and what it does is it automatically opens. So let's take an HTML for example. It creates a report. So all the plots that I defined, it takes it creates an HTML report. If you had selected Microsoft Word, it would have created a Word report right inside SolidWorks where you have all the information, and this report or the files of this report is saved along with your model. So that and it's completely useful if you want to share some design in your design review meetings or share these reports with your customer. You have these things automatically generated. They have the plots, you know, they can be looked at, so on. Okay. So pretty much that summarizes a very short product demonstration of this capability inside EMS. And I'm going to go ahead and revert back to the PowerPoint where I'm going to just go ahead and summarize what was done. Okay. So we're going to briefly now take a look at the various products and bundles that EMS has. Okay. There are two different main types of EMS products that are available. One is called EMS Professional, other is EMS Premium. We also have a high frequency solution which is RF and microwave. Okay. The EMS Professional comes with 5 different types of solvers: electrostatic, conduction, magnetostatic, AC, and transient magnetic. The problems that transformer industries are interested in basically falls under AC magnetic and transient magnetic space. So EMS Professional will be able to do that. We also have several add-ons. Like for example, if you want to study the temperature distribution, you want to couple EMS to a thermal add-on. So it's we couple that to thermal simulation. If you are designing motors and so on, you can couple that to motion. And finally, later this year, we're going to come out with a structural add-on where you will be able to couple, calculate the forces, etc. from EMS, and then bring it on to structural simulation to compute the stresses, etc.
Excuse me, Arvind, this is Adam, Sales Manager again. While you're speaking about the bundles, I would like to mention that we do have an ongoing promotion now of prices for the month of September. Any purchase of EMS gets 40% off, plus free 6 hours of web training, plus free 60 days of application support, direct application support. So I repeat, 40% off, free 6 hours of web training, and 60 days of free application support. Thank you.
Okay. And we have EMS Premium, which contains EMS Professional and the thermal and the motion add-on. Here, obviously, there's a price break when you buy all of them bundled together. That's the EMS Premium. But at any point of stage, you can add on this one to EMS Professional. So really, the simulation that I showed you are the things that you want to do, most people in transformer industry wants to. So what type of products do I really need? So all you need is a SolidWorks, basic SolidWorks 3D, okay, CAD. It could be this one, but we prefer that you have SolidWorks 2013 and above. 2013, 14, 15 is fine. EMS 2015 will work with all of them. You would need EMS Professional and EMS Thermal Simulation add-on. So this is precisely the products that you need to do what I just showed you.
Excuse me to interrupt one more time, Arvind. I would like also to mention that EMS is also offered as an add-in to Autodesk Inventor, which is a full 3D Autodesk Inventor. So if the user is using Autodesk Inventor, not AutoCAD, Autodesk Inventor, he can buy the same package as an add-in to SolidWorks, and it should have the same price, and it does have the same ongoing promotion. Thank you. Keep going.
No problem. And with this, pretty much I want to thank you all for attending this webinar. You know, I would like you to visit emworks.com if you haven't already done so. We have a section for white papers and customer testimonials. We also have a small YouTube channel where we have over, I would say, 50 or 60 videos, several of them pertaining to transformer design and industry as well. We strongly encourage you to take a look at it, and there you can have an intimate understanding of a step-by-step process of how to set up a simulation, how to do these things, which we didn't have time to cover in this webcast. And for any questions related to sales or any product-related information, you're welcome to email us at sales@emworks.com, or please don't hesitate to call us at the 1-800 number that is mentioned in your screen. Okay. So with this, I will turn on the mic to Adam. And
thank you, Arvind, for the presentation. And I would like to open the floor for questions. So whoever has, a technical question or a sales-related question, a commercial question, please feel free to type it in the chat box at the bottom of the screen, and we'll address them accordingly. So We'll give a minute and two for attendees to type in their questions. Please remember that this session is recorded, and this webinar will be posted on our website starting from Monday, and it can always be viewed and downloaded as well and forwarded to other people and shared with bosses and other engineers. We're still waiting for the questions to start coming in. There is a small question.
There are a few questions here I can see already, so maybe I'm going to start answering them. One question is EMS capable of computing eddy currents in the core? Of course, yes. EMS simulation will compute eddy currents, and the core loss or the losses or the temperature rise exists because of this eddy current. So EMS will compute the eddy currents, and it will also give you a vector plot of the eddy currents, and also these eddy current losses are actually also computed. Okay. The other question that we have is pertaining to thermal simulation. How are the temperatures calculated? Okay, so as far as the temperature is concerned, it's very simple. So first of all, where is the temperature coming from? Okay, as you notice here, there are two sources of temperatures. One is the current that is there in the coil. Okay, that's called as the winding loss or the losses in the coil. Okay, that's basically whatever I squared R losses in the coil, and that leads to some temperature, some rise in temperature in the coils, and then the coils are connected through the windings and so on, and there is some temperature. But the majority of the temperature rise that you see here, that you saw in the demonstration also, is basically because of the induced current. Okay, so the core which did not have any current that is applied, actually because of the nature, the AC, the alternating current nature of the applied applied signal, the core, which is made of ferromagnetic material, actually there are some induced currents in the core, and that induced current leads to a loss in the core, which is actually called as the core loss. The objective of transformer designers or people who design cores and so on is to minimize this induced current. Okay, so and one of the ways by which it's minimized is to have laminations in your design, in your core, and so on. So that is the main source of the loss. So this I squared R, or the induced current loss, is then fed into a thermal solver, which then computes the temperature distribution in your entire domain. Okay, and how is heat dissipated out from the solid components is due to is because of the convection. So we specified a convection coefficient. Here the heat is drawn out, and that's the heat dissipation, and it solves the thermal equation to give you the temperature distribution.
Any more questions? Do you see any questions?
There's one question on I think that's probably more of a sales related question, is what are the prices and what are the prices after promotion? So I'm just going to bring up the slide that is relevant to the bundles, and maybe Adam or Rick can go over that.
Yes, absolutely. Rick, can you please go over the prices and the promotion? You there, Rick?
Yep, I am there.
Okay.
Okay, you have the bundles up. Okay, basically what we have here is the MS Professional, which Arvin's been talking about. If you were to look at the list price of that program, you're looking at $18,000 for a one-time purchase. And then the annual maintenance plan is an additional $3,000. So that's a total of $21,000 that you'd be investing up front. During the promotion, which is going to last until the end of this month, you'd be looking at a total investment. Instead of $21,000, you're looking at $12,600. So if this looks like something that you could really benefit from, this month is definitely the time you'd want to do this. That's almost a $10,000 savings. Now, in the case of the thermal add-on, which Arvin was also showing today, the thermal add-on, you're looking at a price of a total of $4,000 for that product with the maintenance. Again, the same, 40% off. You're looking at a total of $2,400 to acquire the thermal add-on. Okay, so it's a very nice promotion that we're running this month. Hopefully.
And please don't forget, Rick, that the free web training, 6 hours, it's at $250 an hour. So you're talking about an amount of $1,250 that the customer will get free. The value of $1,250 in training, and the application support is also free for 60 days. And application support means a customer can share with us his model until he gets to know how to use the software and be more productive then, and so basically we would analyze the model of the customer and present the results to him. So it's like direct consulting or direct application support, and the customer gets used to using the software and becomes productive. So that's really, putting the user right away, making use of the software right away, and getting, his return investment back. Thank you, Rick.
Yeah, that training, Adam, is actually 6 hours, so you're looking at a $1,500 savings rather than $1,250.
Exactly.
Yep. Any other questions from anybody? If you just want to put it in the chat again. Adam, did we want to mention anything about phone numbers for getting a hold of us, or has that been covered?
Yeah, Arvin can bring up that website there too. This page too.
There we are.
So basically, sales@emworks.com or 1-800-397-1557 or 514-634-9797. Well, very good. If you don't see any more questions, Arvin, do you see any more questions?
No. Yeah.
Good. Very good. Well, we'd like to thank all the attendees and for the time and making it to this webinar. We'll be sending a recording of this webinar when it is ready, hopefully by Monday latest. Thank you all, and please keep visiting our website for upcoming events. You all have a great afternoon, and bye-bye now.
Yep. Bye-bye.